In this video, I want to talk to you a little bit about residual analysis. Before we start this topic, let me mention one thing so you make sure you do this at the right time. You have completed your model building. The only time you're going to check residuals is once you have found what you call your best model. So make sure you've gone through your model building first and then do this topic. Too many times students try to get to this topic before finishing their model building and it messes them up. So we're going to use our best model and we're going to create what are called residuals to check the model assumptions and detect outliers. And we'll go through a list of the things we can do in just a second. First, what are the residuals? Well, there are two different ways of writing the models, and you know that I've been spending a lot of time writing them in terms of E of y. And when I write the models with E of y, that's the average of all the y's, this epsilon term on the back drops out. It just kind of goes away. In order to talk about the residuals, we got to talk about the errors. And if you remember, I'm going to draw a very simplified version of this. When we have y versus x, say you have points that are da, 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 and then there's a line or some kind of equation, let me put another point in there, that goes through it that we call the best fitting or the least squares line. How much we miss by, I'm going to change ink color here, how much we miss by this vertical distance here, that's called the epsilon, that's the error. We predicted the price to be up here on our line and the real price was down there. We missed. We missed this guy here by that amount. And so these are the errors, the epsilons, and these are the things we've made our assumptions about, right? We've assumed that they're mean of the epsilons is 0, they're normally distributed, the variance is constant, and that the errors are independent of one another. So these are the things we're working with. Well, let's rewrite this equation. Let's think about the errors as being the real value of y minus what our equation predicts it to be. Now this equation here is assuming we know the values of the betas. And when I say we know, that's assuming we know all the points in the populations. That's when you know beta naught and beta 1 and beta 2. So from a practical kind of perspective, it's if you had every single home ever sold or every single apartment or every single automobile. And we don't. We have a sample. And so we don't know the betas. We have estimates of the betas. We call them the beta hats. We have an estimate of the y-intercept. We have an estimate of beta 1, of beta 2, etc. And so we don't really know the errors, the true errors. We have estimates of them, and that's what we call the residuals. And so the way I want you to think about this, y is the true value of y hat is the predicted value. And so when you get your best model has some equation, some least squares predicted equation. If you plug in values of x's, and you can do this in your data set, I'll show you how to do it in statistics. If you go to statistics and plug in values of the x's, you can see what the predicted value of y is going to be for those x's. And if you subtract that from the y, that's called the residual. It can be positive or negative. Each observation has a corresponding residual. Now we're going to use these residuals to do a whole bunch of things. I'm just going to kind of throw them up here for you. Detect model misspecification. This is actually tied to the mean error is equal to 0 assumption. But did we get the right model? We're going to take a look at, and this is kind of an easy one for us, but we're going to take a look at a way of checking to make sure we specified our model correctly. The most important one here probably is this one, detecting unequal variances. Can I say most important? Yeah, probably will. That's the biggest problem that we're going to run into, or that you might run into when you actually do a residual analysis. Non-normality, we'll check for it. I'll also talk to you about how severe the problem is. Detecting outliers. I'll have a lot to say about outliers when we talk about this section, but there's a couple different ways of identifying outliers, a couple different ways of thinking about outliers. And then once we detect the outliers, what do we do with them? I'll talk all about that when I mention that section. And then detecting correlation of errors. This gets us into a topic called time series, which is kind of an ugly can of worms to open, so I will not be opening that this summer. But the correlation of errors, we have an assumption of independent errors. And I'll mention it briefly, but it's not going to be a big deal to us for what we're doing on our regression project. So I'm going to jump into it. In this first video, I want to do and take on this detecting model misspecification. And then I'll stop and create another video for all the other pieces. All right, so let's detect model misspecification, shall we? Here's how we're going to do it. And for a lot of the things I'm going to talk about in this topic, there are some plots we can look at, and then there's some more analytical techniques. For most of our purposes, however, the plots do a pretty good job. And so we're going to plot the residuals versus the quantitative variables. And so when you see this symbol, this epsilon hat, that's going to be the residual. The X is the quantitative values that you're working with, the quantitative independent variables. We plot those to try to look for certain shapes. And any of these plots that we talk about, there's certain shapes that we're going to be particularly interested in. What we're looking for here, let's see if I'll draw it and then see if you can spot the shape. So occasionally we'll get lucky and get right pretty close to the line, if not on it. All right, so we're looking for patterns in our plots. And so what I want to do, and the way our lines work, or I shouldn't say lines, the way our regression equations work, they're kind of balanced on either side of this zero line here. All right, so when I show you this, do you see the shape? And I hope you're saying no, I don't, because the ideal plot is a random scattering of points. And that's what I've tried to draw here. And it's not the random scattering. The random scattering is what we're looking for. It's not the random scattering that alerts us to an issue. That's the one that we hope to see. But what I want to show you are the common problems that we run into. And so the most common problem, you get a plot that looks like this. All right, now if I say, hey, do you see the pattern here? You should say, oh yeah, I see a curve. And that's going to indicate that an x squared term should be added to the regression model. Okay, now what generates this? Well, let me draw you another picture over here. Let's say our data look like this. Okay, so maybe that's what our data set looks like. If you tried to fit a line through this data, you could do it. It would look something like this, right? Maybe put another point over here so you can see it. It would look something like that. Well, if you take a look at the errors associated with this, and the conclusion we'd come up with would probably be there's some relationship between y and x, or some linear relationship, but it's not a strong one. And of course you're saying, well, of course it's not a strong one. We should use a curve. That's what this plot's trying to tell us, because if you think of it, there's the residual, 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 there's the residual. And so you have groups above, then you have some groups of points below, and then you have some more above, and that's what you're seeing here. Now, we shouldn't have this problem. And I kind of drew on top of that, sorry about this. Our approach should eliminate this potential problem, and I want to explain why. The way that I taught you model building, we are what are called build downers. We start with a complete second order model, and then we test different pieces of it and drop them out if they don't work, right? That's what a build downer does. Starts with everything and then takes out the pieces they don't want. You start big and remove pieces until you get down to the smaller model. Sometimes it's referred to as the most parsimonious model, if I want to throw a big term at you there. But being build downers, we start with the the quadratic terms in. We put them in our complete second order model, and then we test for them. So if you have a curvilinear relationship in the model, think about this now. If you have curves, if your data need curves, what do you think you're going to do when you test for the curves, for the quadratic terms? You're going to keep them, of course, because you need them. And if you have a curvilinear model, if you have a quadratic model and your data requires it, you're going to get a nice random scattering when you look at this plot. So being build downers, if we need quadratics, we kept them and we have the ideal random scattering. If we didn't need the quadratics, we got rid of them. But then we'd still have a nice random scattering. So the approach that we're using, if you've done your model building correctly, you should be able to look at your plot and not have a problem. Our build downing eliminates this problem. So what the build uppers will do, and the build uppers are the people that start with a model and they start throwing terms in it. They'll say, well, why be a build downer? Why start with that mess? You can look at a plot like this, and that'll tell you whether you need to square it or not. So just put x in it, and if you see this plot, add x squared. It's simple. And so build uppers will point to this plot and indicate that there's ways to know when to add things. And in the case of a quadratic term, that is correct. But in the case of interaction, there's no plot you can point to say, oh, definitely add interaction. And so the build downers, us, we're going to put interaction in and test for it. The build uppers, they're going to flip a coin. They have no leg to stand on and say, well, you can always, no, you can't. There's no easy way to identify when interaction is in the model. And so we like our build downing. We also like the fact that we can make our decisions based on p-values, which are pretty straightforward and easy to work with. And it takes this detecting model misspecification issue off the table. We don't have to worry about it at all. So that's the first tool, or I shouldn't say first tool, that's the first thing we can do with the residual analysis tool, detect model misspecification. So it's a simple plot. You're going to do a plot of the residuals versus your quantitative independent variables. In your projects, you just have one, but I want to see that plot, and it should be a nice random scattering, and all should be well with your world. So the next step is to take a look at unequal variances